Our first speaker in this session is Théophile Wallez, and he'll be speaking about formally analyzing a cryptographic protocol standard.
Thank you for the introduction. So today I will talk to you about what I've done during my PhD, whose goal is to become a cryptographic protocol analyst by producing a machine-checked proof of MLS, which is a secret group messaging protocol standardized as IETF. And as the adage says, the journey is more important than the destination. And throughout this journey, I found flaws in MLS and helped the working group to fix them before its standardization. I identified and filled gaps in formal security proofs. That is, they don't deal properly with message formats. And I improved the tools to be able to conduct such an analysis by improving the tool called DWASTAR. And during this talk, I will share with you the lessons I've learned throughout this journey, both for protocol analysts and for protocol data designers, that is, how to best cooperate. So before diving into the heart of the talk, let's talk about how do we analyze a cryptographic protocol. The most traditional tool we have is to produce a pen and paper proof that the protocol is secure. So this is effective, but it requires expert humans to check that the proof is correct. And so to solve this problem, we can produce a machine-checked computational proof. So now a computer is checking the proof, but it is very hard to convince a computer. So this comes with limited automation, and it is difficult to analyze large protocols. And so to solve this problem, we can use machine-checked symbolic proofs. It has good automation with the trade-off that the symbolic model is less precise than the computational model, but still, symbolic proofs had many successes during the last decade. Hence, we choose this method to analyze MLS. To be more precise, our approach we develop to analyze MLS is that we take the MLS specification written in English in prose and translate it into a precise mathematical specification in the F-star proof assistant. And then we use DWASTAR, a symbolic analysis framework, to do security proofs. But how can we be sure we did no mistakes during the translation? To increase our confidence that the translation is correct, we use HackerStar on our specification. We obtain a bit-precise executable implementation that we use to run interoperability tests. And the result is that we increase our confidence that our specification correctly implements MLS, hence that our security proofs actually deal with MLS and not some subtle variant of it. So now that I gave some overview of our methodology, let's talk about the analysis itself. In short, what we have done is that we took the MLS protocol written in 120 pages of English. We showed how to modularize it into 3 sub-protocols, which we called TreeSync, TreeChem, and TreeDem. We found various design flaws and helped the working group to fix them. And we proved security theorems about TreeSync and TreeChem in the symbolic model, and TreeDem is still future work. So in our modularization, TreeSync is in charge of group evolution. That is, throughout the lifetime of a messaging group, participants can leave and join a group, and TreeSync deals with that and maintains an authenticated state, which internally is a tree that apparently grows upside down, and gives this state to TreeChem. TreeChem is in charge of updating keys and rotating them, which provides to MLS strong confidentiality guarantees, such as post-compromise security and forward secrecy. And TreeChem gives these epoch keys to TreeDem, which is finally in charge of sending and receiving messages. This modularization was crucial for us because it allows us to analyze the protocol modularly, and analyzing MLS as a single monolith would have been too difficult. And at the beginning, it was not possible to modularize TreeSync and TreeChem like this. Indeed, the guarantees offered by TreeSync were too weak, and it was difficult to analyze it standalone. So we discussed with a working group and ended up doing about 30 lines change in the specification that strengthen the guarantees of tracing and allowed us to analyze it as a single interesting protocol. So this leads me to my first lesson for protocol designers: modularize your protocols. Of course, it's easier said than done. So I encourage you to chat early with a protocol analyst in the design process, see how they would modularize your protocol and what you can do to improve the abstraction boundaries. So this will make the life of analysts easier. As a bonus, I think your protocol will be easier to understand because I think readers want to have some kind of mental model on why the protocol is secure. And it will also help implementers by showing them how to implement your protocol modularly. We started by proving security theorem for tracing. We prove an agreement theorem, that is, members agree on the group state, which in particular covers group membership agreement. Everyone agree on who is in the group, which is important because you want to make sure that an attacker cannot be in your messaging group without your knowledge. And our proof relies on minimal assumptions on trichem and tridem. However, at the beginning, these assumptions were not true. So this could be used as a first step to create an attack on MLS. The problem here is that in tracing, we have a signature, and signatures don't operate on high-level types, they operate on bytes. So we need to serialize the signature input to bytes. And tridem also relies on signature with a different high-level types for signature input. The problem here is that tracing and tridem rely on the same signature key, but use different type for their signature input, hence different serialization functions. And so what may happen is that a signature input in tridem and in tracing have the same serialization, meaning that even though it's different types, they have the same bytes representation. And in that case, we can use a signature in tridem to forge a signature in tracing. So we notify the working group, propose the fix that was accepted, and now this attack is not possible. So that's good. So this signature ambiguity raised two questions. The first one, from the protocol designer perspective, how did this attack survive so long? It's a well-known problem in the cryptographic community known as lack of domain separation. And so I think the problem here is that there is no rigorous definition for what is domain separation. As far as I know, it means sprinkle tags in serializations to avoid problems. And also domain separation is hard to enforce in large standard because here the signatures are pages apart in the specification, and you cannot really skim through the document to find the problem. And second, from a protocol analysis perspective, each time we find an attack on a protocol that was analyzed, we have to ask the question, why was this attack missed? To answer this question, we must first say, what does it mean to prove that MLS is secure? So what is a security proof? We translate the MLS specification written in English into a mathematical model. Then we prove security properties on this mathematical model. And so there are three places where we can miss the attack. Either the security properties don't catch this attack, either there is a problem in the security proof, or maybe the mathematical model is imprecise, meaning that it is secure against this attack, but the actual protocol is vulnerable. And that is what happened. In mathematical models of MLS, we find that there is no message formatting, there is no serialization. Signatures operate directly on tuples, hence they miss this message formatting attack. So this leads me to my lesson for protocol designers, analysts. Reason on precise mathematical models. It will allow you to catch subtle attacks such as message formatting attacks. And as a bonus, in our case, it also allows us to provide a reference implementation. So I think it's not breaking news. People already know that we don't deal with message formatting in security proofs, because it's boring and it would make proofs more complex. And as a fun fact, I once had an analyst that told me, yeah, each time I do a reduction, I do realize that the encoding of these tuples must be important, but I really, really want someone else to think about it. So thankfully, I am someone else, and I did think about it. And I propose a solution in 3 steps. First, we define a rigorous definition of what is a secure format, then such that secure formats can soundly be abstracted away in analysis, and we make a tool to check whether these formats are secure. So we do a little bit of detour through security critical formats for cryptographic protocols, and we'll go back to MLS later. So although our example is on signature, the problem is everywhere in cryptography. Every cryptographic function takes as input bytes, and the cryptographic assumptions we have are when we use them with bytes. However, the security properties actually used are when we use them with high-level protocol data. And we see there is a gap here, which is filled by the study of format properties. So in our paper, we propose definitions of security properties for message formats, and for several cryptographic functions, define what is good domain separation. And for signatures, we define good domain separation as the formats used with signatures must be injective, that is parsable. Otherwise, if M1 and M2 have the same serialization, you can use a signature on M1 to forge a signature on M2. And furthermore, for each signature key, we must decide on only one format to use that must not depend on external context, because otherwise we have a problem as we had in MLS. You can take a signature done with one format to forge a signature done with another format. And this, if your signature key will be used in future versions and extensions of your protocol, you must make sure that this property stays true, and you must design your format in a forward compatible way. And the next thing about this condition is that it is sufficient and necessary. It is sufficient because if your format obeys this property, you can reduce the security properties you want to use on high-level types to the security properties, the security assumptions you actually can make on bytes. And it is necessary because if you don't obey this condition, there is clearly something fishy going on, and maybe you have problems, or your security proof will be very hard to make considering these issues. And so we may ask, is it difficult to create a format with these properties? And I claim that in real-world protocols, when some data is sent on the network, it will obey this good domain separation property because it must be passed. And as an example, if you look at the TLS13 handshake message, it's a tagged union, and the tag is designed in a way that it can evolve throughout different versions of TLS. So this handshake type here exists since 1996. So I claim that the TLS13 handshake message is well domain separated since I was born. So we have all the engineering and process and best practices to design such message formats. And I think we should apply it for formats of cryptographic functions. And actually, when we design a message format for a cryptographic function, such as a hash, there is little care given to it. For example, the transcript hash is defined as, well, let's concatenate every message and it will be fine. Actually, are we even sure that we don't introduce a collision before even hashing? So here, actually, it's fine because every message has internal length tag, but still, if this list of messages had to be parsed, you would never define it like this. So this leads me to my lesson for protocol designers. Please love all message formats equally, whether it has to be parsed or if it's an input for cryptographic functions. If you do that, you will rule out a whole class of attacks, that is message formatting attacks, but also cross-protocol attacks, at least some kind of protocol attacks. And you will tremendously help protocol analysts that are willing to model message format properly. We now go back on MLS with our analysis of 3chem. So we proved a confidentiality theorem on TreeChem. And the main challenges here are that TreeChem relies on recursive data types, that is trees. So the proof must be inductive, and TreeChem relies on an unbounded sequence of key derivations, unbounded sequence of public key encryptions, all of this within a tree. And so I think that it's currently out of scope for automatic symbolic provers. And TWASTOR is really a tool of choice because it was designed initially with these challenges in mind. So initially, TWASTOR was not able to prove TreeChem, and we had to heavily improve it and manage to do our proof, which means that in addition to have a security proof for TreeChem, we also have, as a byproduct, developed a tool that is capable of proving such a protocol. And so this leads to a lesson for protocol analysts. New protocols may require new tools. And I can't think we can have one tool to rule them all. I think we always will have different tools. And I think it's fine because pen and paper people also have different tools. And today, TWASTOR is a good tool for TreeChem-like protocols. And maybe tomorrow, we will have a new protocol that is out of reach of every method we know to produce a machine-checked analysis. And we will have to design a new one. And I think it's fine. So to conclude, I made a good step towards the destination of my PhD by proving two subprotocols of MLS. And during this journey, I developed a methodology to reason on precise mathematical models of cryptographic standards. I showed the importance of message formatting in cryptographic protocols and proposed a rigorous definition for domain separation. And finally, I heavily improved a tool to produce such analysis, and which means that now we can use it for other analysis. So I thank you for listening, and I am ready to take questions.
All right, we have microphones, I think, on all aisles of the room, so please feel free to come up to the microphone if you have a question.
There is an alternative to proving the full correctness of a protocol, which is less ambitious, but might be more widely applicable. And this is to try to compile a list of all the known types of attacks, like the domain separation problem you mentioned. So assuming that you have this very long list of known attacks, do you think that it will be easier to automate the process of showing full checklists that the new protocol is not susceptible to any of those? We are doing it, for example, in cryptanalysis, where we know about differential cryptanalysis, linear cryptanalysis. We have a list of things, and every new crypto system is shown not to be susceptible. So how about doing this less ambitious, but potentially more applicable kind of just a checklist that the new protocol is not vulnerable to any of the known attacks?
Yeah, so thank you for the question. So I think the different criterion we designed for different cryptographic functions are easy enough to check. So the methodology, so I didn't really dive into it, but I think is like in a protocol, let's gather every signatures performed in the protocol. And so each time I have a signature key, check the format and see if it obeys the property. And you can do the same for other functions like AEID, MAC, KDF. It's also similar criterions. And I think just needs to actually make the effort to gather of this usage and check the message format.
Thanks.
Yeah, thanks for the talk. So I'm interested in the problem of taking a pile of natural language in, say, an IETF spec and sort of translating that into the model. If you can do one thing to improve the IETF spec, what could people developing IETF specs do better in your opinion?
Well, I don't have a good answer for that. My process to create the specification was to struggle reading through this document while at the same time learning cryptography. So it may not be a good example. Yeah, I don't know. We'll need more time to think about this.
Good.
I'm afraid we need to move on. So please join me in thanking the speaker for the talk.